In this video, I'm going to go over a special case of the conservation of energy equation that really is more applicable to engineering type problems. And it's the form that we'll typically use in this class to solve problems where you need to address the conservation of energy. So what we do in engineering often is we're not so much concerned about what happens inside the black box here, but more in the endpoints. So if we start at point 1, stuff goes into the system, stuff happens to that stuff, and then it comes out, ends up here at point 2. And that stuff that happens inside the black box in our case is going to be heat added to the system, there's work done, and then there's losses that occur due to valves, bends in pipes, and things like that. And so what we want to do is kind of group all those things together and deal with it that way to simplify some of our engineering type problems. Okay, so the simplifications for this particular formulation, there's 3 major ones that you need to be aware of. The first one is we're going to assume that the flow is steady. And as you recall from our previous discussions, what that means is we're going to assume that the time rate of change of the integral over the control volume of rho e dv is equal to 0. So that term just goes away from our conservation of energy equation. That's a big simplification right there. The second thing we're going to do is assume that P over rho plus GZ plus U is constant across the pipe cross-section, or the conduit cross-section. What that allows us to do is pull out the energy term, the little e, which is P over rho plus GZ plus U, out of the integral. So what that leaves us with, so if we pull that out of the integral, this becomes P over rho plus GZ plus U times the integral over the control surface of V over 2 squared V dot rho dA. So we pulled all that out. And the next thing we're going to do is we're going to add a correction factor to the kinetic energy term to account for the non-uniform velocity distribution. So we're going to go ahead and say, look, we know it's non-uniform because there's things like the no-slip condition at the wall of the pipe or conduit, so the velocity is 0 there, and there's going to be some maximum somewhere in the flow. Okay, so what that looks like is we're going to say that this term here is going to be alpha v bar squared over 2. And then that alpha is just going to take into account, if we do the integral over that surface, the alpha is going to take into account how that shape plays out in the integral. So, and what that really means is that alpha is going to equal 1 over the area, the integral over the area of v over v bar cubed dA, and that leads to alpha equal to 1 for uniform flow. Right? And so that intuitively makes sense, right? So if there's no variation in the flow, we get alpha equal to 1 when we pull back out our equation. However, we know again that the velocity is not uniform. We're just going to plug that alpha in. And by using that alpha for particular shapes of conduits, we can pull the v squared over 2 term out of that equation as well. And we end up with something that looks like this. P over rho plus GZ plus U plus alpha V squared bar squared over 2 times the integral over the control surface of rho V dot dA. We can then say that this is just the mass flux, or m dot. Okay? We can now take these simplifications and plug those into our conservation of energy equation. I'm going to move that m dot over, and for reasons you'll see in a minute, and rewrite our equation. All right. So with our assumptions, the Reynolds transport theorem and conservation of energy equations will look like this. We have 1 over m dot times q dot plus WP dot, work done by the pump, minus the work done by a turbine. And then I'm going to go ahead and add in a loss term, which is all these losses that I talked about in the beginning. So it's going to be WL dot. so it's just work done by losses, is equal to the summation of plus or minus m dot times p over rho plus gz plus u plus v bar squared over 2 alpha. All right, so that is a condensed, simplified form of the conservation of energy equation, where this term here is just the integral. So I've taken that integral, it's just going to end up being m dot, and then we want the difference between the control surface 1 and control surface 2, and so it's just the summation of our control surfaces of plus or minus m dot times our quantity for our energy. Okay, so I want to make another simplification here, and because in engineering we often quantify all these things not in terms of the energy per se or the work. We talk about it in terms of head, which is a length scale. It's kind of a measure of the height of the fluid, so it's a kind of a measure of the potential energy in the system. And so what we do is we often describe energy in terms of head, which again is a length. And we have pump head, turbine head, and head losses. And what those look like, if we write out our equations, we define HP is the pump head, and that's going to equal W dot P over M dot G. Same thing with the turbine head, so H sub T is going to be equal to W dot T over M dot G. And if you work out the units, I'm not going to do it here, you'll see that that's in a length, or meters, or feet. And then finally we have these head losses. And it's losses due to friction, bends, valves, etc. We're going to group all that stuff into a single term that like I did before, and we're going to say that H sub L is equal to WL dot over M dot G. Okay? So if you look back at the previous equation, you'll see that we have 1 over M dot already times W dot P, W dot T, W dot L. And so if we divide through by G, we can back out these head terms and replace those. And so we're going to go ahead and do that and reformulate it like this. All right. So again, I'm going to divide through by gravitational acceleration and replace the work rate terms with our head terms. So we're going to end up with Q dot over M dot G plus H sub P plus, now I'm going to go ahead and rearrange the two surfaces. So surface 1, control surface 1 and control surface 2 plus P1 over gamma. Remember, it was P over rho, but I divided through by G, so I have P over rho G, which is gamma, plus Z1 plus U1 over G plus alpha V bar squared 1 over 2G is equal to H sub T plus P2 over gamma plus Z2 plus U2 over G plus alpha V2 bar squared over 2G plus H sub L. And so in this formulation, on the left-hand side, we have energy in, and this is going to equal energy out, right? So that is the engineering formulation. And what you'll notice is now we have everything in terms of a single variable. There's no integrals left. We've made assumptions to get rid of those, and we can just plug in numbers if we can choose our endpoints well, such that we don't have to do a bunch of arbitrary shapes and things like that. Okay? Before we finish this video, I want to look at one special case of this conservation of energy. And so we're going to look at a case here where there's no pump, no turbine, no losses, all right, and no heat transfer. All right, just like we did with all of our problems, we'll go ahead and write out again the full equation. So we have Q dot over M dot G plus H sub P plus P1 over gamma plus Z1 plus U1 over G plus alpha V1 bar squared over 2G is equal to H sub T plus P2 over gamma plus Z2 plus U2 over G plus V1 bar squared over 2G plus H sub L. Okay, there's our full equation. And now we're going to look at our special case here. All right, so no heat transfer. Okay, that means that this term is 0, right? There's no pump, so this is 0. All right, so if there's no change in the heat in the system and no heat transfer, then we can say this is U1 is equal to U2. So those terms cancel. All right. Then we can say that there's no turbine, so that's 0, and there's no head losses, that's 0. All right. And rewrite it again. So now that we've gotten rid of our terms, we say P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G. All right, and I made one more assumption here when I wrote this, and I assumed uniform flow, so I set alpha equal to 1. So that's one thing that we didn't explicitly mention, but I went ahead and did that. And what you can see here by doing so is we end up with the Bernoulli equation. So we end up in the same place. We got to from a completely different angle, and it just shows you that the Bernoulli equation is consistent with things like the conservation of energy. And so I hope you can see now that this formulation is going to be extremely useful when we look at engineering problems, and I'll go through a couple examples of those in the next couple of videos.